Good morning all and welcome to first annual workshop on data sciences here at Tennessee State University. My name is Ali Sekmen. I'm the chair of the computer science department. Also, I'm the chair of the workshop for this year. Tennessee State University is going to hold annual workshop on data sciences every year with a different focus. And this year the focus or the theme of the workshop is subspace clustering and high dimensional data analysis. And we have a very exciting program for today, actually. And as you know, data sciences deals with extraction of useful information from data. And data, in many cases, may be very complex and large, and that traditional data processing techniques may not work. And subspace clustering is one of such problems. Today, we are going to have 11 speakers, and 2 of them are keynote speakers, Dr. René Vidal of Johns Hopkins University and Dr. Akram Al-Groubi of Vanderbilt University. And we also have 11 invited speakers, and most of the speakers are going to either talk about subspace clustering or high dimensional data analysis or both. And yesterday we had 2 mini lectures, and if you participated in yesterday's program, which were mainly for non-mathematics faculty, we introduced the subspace clustering problem. We talked about some fundamental concepts like PCA and spectral clustering. They may be very useful for today. So I'm very happy that that you are here today. I'm hoping that by the end of today, you will understand what the problem is, specifically subspace clustering problem. And you're going to understand what is the state of the art in this area. So that's the whole goal of today. And I am very pleased to have our first keynote speaker, Dr. René Vidal. He's a very well-known and recognizable person in subspace clustering and high-dimensional data analysis with a lot of impactful publications. Actually, I assure you that you're going to enjoy his talk because I participated in 2 of his talks before in the recent years. He does not just talk for the sake of talk, but he makes sure that you understand what he's talking about. And I must say that I really enjoyed his talks and I learned. So I'm expecting the same will happen today. Dr. Vidal is an associate professor in the Department of Biomedical Engineering at Johns Hopkins University. And he has MS and PhD degrees in electrical engineering and computer science from the University of California at Berkeley. And he co-authored more than 180 publications in different areas spanning biomedical image processing, computer vision, machine learning, robotics, and signal processing. And I happen to read many of his publications, and they are really good publications. I strongly recommend that you do the same. Dr. Vidal is an IEEE fellow, and I think that's by itself is an accomplishment, because being an IEEE fellow at this young age is an accomplishment in my opinion. He is an associate editor for IEEE transactions on pattern analysis and machine intelligence, which is the top journal in this area. And he's also associate editor for a couple of other journals. As far as I remember, one of them is Journal of Mathematical Imaging and Vision. Another one is Biomedical Imaging, I believe. So also he was the chair of many impactful conferences, mainly on computer vision in the recent years. And he has best paper awards in some impactful conferences as well. And today, he's going to focus on, his talk is going to focus on algebraic and sparse subspace clustering techniques, specifically tailored for high-dimensional data analysis. With that, I would like you to pay full attention to him and help me in welcoming him to the stage. Dr. Vidal.
Can everybody hear me well? So thank you, Ali, very much. It's really an honor and a great pleasure to be here. I think it's a fantastic idea to have organized a workshop in these areas. I think it's very timely. And I look forward to talking to many of you and about these topics, which is one of my passions. So, as Ali was saying, I think we live in a very, very exciting time these days. Data is being collected at an unprecedented rate. It used to be the case that in the 60s and 70s, we had lots of models and not too much data where to validate them. Today, the situation is exactly the other way around. We've got lots of data, and we have no idea how to make sense of it. And this is true particularly in areas that involve images, like computer vision or astronomy. But it's also the case in medical imaging, as well as in computational biology. So why is it so? And let me give you a little bit my experience in computer vision, which is the area that is closest to my heart. So this is the number of images that are acquired every year, starting in 1826 with the first image taken in France, all the way to the order of about 380 billion images per year. Obviously, digital versus analog, there's been a dramatic change. And part of it is social networks. So as you can imagine, everybody is just taking pictures and uploading them. It used to be the case that I was up to date, and so Facebook was the main thing. But now there is all of these other things, like WhatsApp seems to be taking the market in terms of the number of images that are uploaded every year. And I'm sure the undergraduate students know what I'm talking about, even though I don't. So Facebook, for example, has about 350 million photographs that are uploaded every day. And it's been accounted that there are on the order of 3.8 trillion images that have ever been collected by humanity. I wish I knew how they counted them. But the same thing is true about videos. This number, every time I give the talk, it changes. And in fact, I just gave it about 2 years ago, and that number of 300 hours video per minute was only 100 about 2 years ago. So what's most scary, in fact, is that if I talk about images, 20% of all the images were just taken last year. And if you look at the images that were taken in the entire 18th century, it takes about 2 minutes today to take that many images. And for videos, it is predicted by Cisco that by 2017, 90% of the traffic in the internet is going to be video. Therefore, this calls for statistics, mathematics, machine learning, to develop techniques that are going to be able to make sense of vast volumes of high-dimensional data. How can one do so, and what are the basic mathematical models that are going to be useful or that have been useful over the last decade? I think the idea that even though the data is of very, very high dimensions, and in the case of images, this is the number of pixels, the intrinsic dimension of the data is much lower. So, for example, if I take pictures of you, and you are, all I do is to change the illumination conditions all over the place. Under very simple models, you can show that this is a three-dimensional subspace of the ambient space dimension, okay? And the very simple models in computer vision would be something called Lambertian, which is a property of how the light is reflected in materials. And there are slightly more complicated models. That subspace is 9-dimensional. So what that means, if I take all of the faces of you and they're all lighting, there will be some 9-dimensional subspace in, say, R1 million, when 1 million is the million pixels in the image. Likewise, this is going to be another subspace corresponding to another individual. So if the question is, I give you all of the pictures that have been taken of you, and I tell you, just divide them into multiple groups that correspond to the faces of different individuals, that is a problem that can be tackled with this idea of clustering the data into multiple subspaces. Here's another example. You take images, and a lot of the analysis in computer vision these days is based on looking at local patches. And so as you can see, there are different regions. Everything related to the zebra is one texture pattern. If you look at the water or the grass in the background, there are different texture patterns. Again, it is possible to say that the space of all these patches lives in a low-dimensional subspace. Not all textures are low-rank, but many of them are. And therefore, if you ask the question, can I divide this image into different regions corresponding to different textures, one potential approach is to say, use clustering in terms of subspaces, with one subspace associated to each texture. This is another example where you take videos, and you see some little dots, hopefully. So there are some red dots in one car, blue dots on the other, and yellow dots in the background, and the camera is shaking a little bit. So what if the task is separate this video into the different moving objects in the scene, the two cars and the background? So if you look at these points that I've drawn there, so these are trajectories in time. If you think of those trajectories as vectors, again, you can prove in computer vision that those vectors live in a four-dimensional subspace. So there is a subspace associated with each moving object, and the segmentation can be done using subspace clustering. Another example that we worked a while ago is what if you now have this very deformable type of videos where you've got fire on top of water. And so if you look at one pixel on its own and you look at the evolution of that pixel as a function of time, it will describe some trajectories. That trajectory, again, lives in a low-dimensional subspace. The reason being, say, if you model that with some differential equation of some order, if it is a linear differential equation of order n, you can associate a linear subspace of dimension n with that. And that is why subspace clustering is useful. It can be put together with techniques from dynamical systems for addressing these kind of problems. And the last example I have here, this is from either the past or future candidates, but this was a couple of years ago. So if you have these videos, if you look at all the collection of frames, say of Obama or of the public, even though there is some variability, right? They are moving, the camera is zooming in and out, they can be well approximated. You know, if you think of every image as a vector, and you think of all the collection of vectors associated to Obama, they can be well approximated by a low-rank subspace. So the question of dividing these videos into multiple video clips, again, multiple subspaces, one per video clip. All right? So having motivated various applications of subspaces, what are the fundamental tasks we are interested in? One of them is clustering, which I've already motivated. But the other one might actually be classification. Suppose in the case of faces, I not only tell you, here are the faces, but as you've used many of the software, right, you can annotate the faces. The same thing is true in Facebook. You can put names and tags to it. So if you had both the images and the tags, and that's what I mean here, I know these are all the images of one individual, these are the images of another. I give you another new image and I ask you which class it is. Can you exploit the subspace structure to do better classification? That's another problem. So today I'm mostly going to focus on this problem, and thinking that some of you are experts on this topic and have worked on it for many years. Others have learned a little bit, and others is the first time you're hearing about this. I've tried to do a very broad overview of the field. So I will start with an introduction, which is going to take the last 15 years, and I'm going to spend 15 minutes trying to give you a summary of what is the state of the art. What are the big type of approaches that have been tried. And then I will focus and give a little bit more of the mathematical details for two types of approaches. One that is mostly coming from algebraic geometry, and the other one that is mostly coming from techniques in signal processing, sparse representation, and convex optimization. And towards the end, I'll show you some examples of how these techniques work in practice. So let me start with an introduction. So what is the problem? And many of you who came yesterday, you already know this. But abstractly stated, I give you a cloud of points in a high-dimensional space, and you know that they live in a union of multiple subspaces. And a priori, you might not know how many subspaces there are. You may not know what their dimensions are. You don't have a basis for every subspace. And more importantly, you don't know which point belongs to which subspace. So in principle, all of these quantities are to be estimated just from the given data. Okay? So that's the abstract formulation, but there are many challenges when trying to look at this problem. So the first one I've put here is the issue of model selection. When we look at many statistical techniques, right, we always say parameter estimation, and here's my parameter, and this is the dimension of the parameter. Here, the question is, well, I don't know how many subspaces there are. So the number of mixture components in a statistical model might be unknown. But I don't know their dimensions either. So the question of model selection is a very fundamental one, and not a lot of work has been done in that area. So it continues to be an important challenge. The other one is that you have, from the estimation perspective, two types of variables. some that are continuous, like what is the basis for the subspace, some that are discrete, which point belongs to which subspace. All right? And so there is this combinatorial type of problem, and in fact, it's very easy to see that in general, this problem is exponentially hard. And therefore, developing techniques that are able to solve it in an efficient manner and can tackle the combinatorial nature of the problem is a very important challenge. But in addition, the picture is never as perfect as I've drawn it. So you have corrupted data. The data will be just approximately lying in subspaces. You will have outliers, points that are all over the place, or you might have, you might take one point, but only one entry or two entries of it are completely corrupted. Okay? Why could that be the case? Well, think about faces again. What if you're wearing glasses versus not wearing glasses? What if you're wearing scarves versus not wearing scarves? What if in those videos with moving objects, a piece of the, one object occludes the other? So these trajectories are now not even complete. So you actually have also potentially missing entries. And particularly in the case of computer vision, this comes due to occlusion. So that's another set of challenges, dealing with corrupted data. But other challenges, which people don't mention as often, have to do a little bit with the geometry of the problem. And so here I've plotted that with two databases. So in this first picture, the x-axis is the angle between the subspaces, or the so-called subspace angles or principal angles in linear algebra. So I have two subspaces, and in this case there is just one angle among them. So the x-axis goes from 0 to 90 degrees, and the y-axis is, this is a database. So in the database I take pairs of subspaces, and I ask what is their angle. And so what this is the percentage of pairs whose angle is less than or equal to something. Okay? So this is trying to tell you in real data, are the subspaces very close or are they very far? So the blue curve is the database with videos with moving objects. And most video sequences are between 0 and 5 degrees angle. Why would that be? Well, when the guy is videotaping me and I'm moving around, right? What does he do? He tracks me a little bit. So the motion of the camera, which is the motion of the background, is very correlated with my motion, right? Or if I'm looking at humans moving, there is a lot of correlation between the motion of different limbs. So the subspaces end up being related to each other, and you can see that by having small angles. All right. The other curve is for faces. If I take all of my faces under varying illumination, and I take all of Ali's faces, how far apart they are in terms of the angle. So this picture says that they are between 10 and 20 degrees, so not much. Okay, so that's another challenge. That's important. The other one, which you might say, well, is this a really different clustering problem than usual? In the sense that typically we can cluster based on my neighbors. My neighbors are nearby, and I likely belong to the same class of the neighbors. So if I look at this one, right, this point here is very far from that point, right? And they're in the same group. And then these 2 points are very close, but they're in different groups, right? So the issue with clustering is also what happens near these intersections between the subspaces. And so this is exactly what this picture is trying to tell me. It's like, look at your k-nearest neighbors and tell me how many of them are in the wrong group. So this is exactly this axis, how many nearest neighbors there are, and here is the percentage of points in the wrong groups. So for video, it's not too bad. So if I look, say, at 10 nearest neighbors, about 5% of them are in the other moving object. And that makes sense because in videos, unless objects are crossing through each other, they are in different regions of the space, so the data tends to be a little bit more separated spatially. But for faces, if I look at the 10 nearest faces in Euclidean distance, about 65% of them correspond to another individual. Why is that? Well, think about a face of you with a lot of light, all right, and another face of you with very little light near the intersection. They are very far apart. It's much more likely that two faces of myself and Ali are very close at the same level of illumination that across different levels of illumination. So that is why if you only do nearest neighbors, you may fail. Okay? So these are the key fundamental challenges. So if I look at the last 15 years, what are the kinds of approaches that people have tried to come up with to look at this problem? So the first family of methods, you look at this and you say, aha, if I knew which point belongs to which group, then it reduces to classical PCA, because I can just do PCA for every group, so I could estimate the basis. The other way around, if I knew what is the basis for each subspace, I can cluster the data, because I can assign every point to the closest group. So why don't I just do that? I'll start with some random guess as to what the segmentation might be, and iterate between assigning points to subspaces and re-estimating the subspaces up until convergence. And you can prove that this method actually converges. In fact, it converges in finitely many iterations. Right? There are two ways of doing this. One is using nonlinear optimization, and that's the method called K-subspaces, which is effectively a nonlinear, non-convex optimization problem, which effectively follows more or less the same steps that I just talked about. But there is also a way to do this, in a probabilistic setting where I don't do hard assignments of points to subspace, but I just say what is the probability that these points belong to this subspace. So that is done with generative methods, and is therefore done using methods for estimating the parameters of a mixture model in statistics. So this is essentially, for those of you who are familiar with that, the expectation maximization algorithm for estimating the parameters of a mixture model. All right, so, well, that sounds great. Why don't we just do that? Right? In fact, this seems like very simple, very intuitive, and probably for low-dimensional subspaces, not too computationally complex. I just need to do one PCA per group, which more or less has to be the complexity of it in any case, and maybe the only challenge is that I might need to iterate many times. So true, it is simple and intuitive. Another thing that is usually overlooked in the literature is that at least the probabilistic approach can handle missing data because it's latent variables. So you can have two latent variables. One might be which subspace you belong to, which is the one I was referring to so far, but another one might be, well, these pieces of the data are unknown, I want to estimate them as well. So you can do EM with missing data for this problem as well. But the challenge is that the optimization problem is non-convex. And so, as you iterate, you converge, but you converge to a local minimum. And experience shows that unless you initialize it very well, you may converge to a very bad local minimum. So to get good results, you need to try many times. For other problems like k-means, there are good ways to initialize. For this, there is a lot of research, and I think things are getting better. But at least as of 2000, at the beginning of the 2000, techniques for initialization were not very good. The other issue is that I need to tell the algorithm before I start how many subspaces there are and what are their dimensions, because it's parametric estimation, so I need to tell what the parameters are. Surely enough, in modern statistics with non-parametric methods, I can put now hyperpriors on these parameters, and there is certainly work at trying to address these issues using probabilistic techniques. Right? So that's the first family. Nice, simple, intuitive, but issues with local minimum. So when I began working on this, that was the state of the art, and I was puzzled by this question. Well, this is chicken and egg. Given the segmentation, I have to estimate the subspaces, and I have to go back and forth all the time. So I was looking at this picture over and over and trying to say, well, how can I do better? How can I get rid of this need to alternate, which seemed to be sort of inherent to the problem? And so if I look at this picture, and I visualize it always, what about if I had two lines, right? We all know how to fit a line. What if I had to fit two lines at the same time? And eventually, the idea came up that, aha, what about thinking of this from an algebraic geometry perspective? Rather than thinking of this as just a subspace, think of it as an algebraic variety. So I have polynomials that are zero on the union of two subspaces. And I'll discuss that in much greater detail in a minute. But for the time being, the main point is that a union of subspaces is an algebraic variety there is a collection of polynomials that vanish on all the data points. In fact, the degree of the polynomial is the number of subspaces. And the roots or the factors of the polynomial have to do with, correspond to each one of the subspaces. In particular, I'll explain that in more detail, they encode normals to the subspaces. Okay? Therefore, what this brings is a new avenue where just fit polynomials to the data and then factorize the polynomials. And therefore, ideally, in closed form, you can get a solution to this problem without having to ever iterate. Modulo, of course, that there is some roots in one variable that need to be solved at some point, but suppose that that was done in closed form, which can only be done for degrees less than 4. Okay? So that was sort of very cool, like in principle, very elegant and very nice. And so 2 techniques were done. The one I was referring to mostly is GPCA, which actually started in computer vision in '91 for very different kinds of problems. They were looking at fitting multiple motions to transfer. It's like, say you're looking at a swimming pool and there is something moving and you want to do segmentation. So over there, instead of being polynomials, it was higher order partial differential equations. So that was a paper by Japanese in 1991. But other than that, most of the work really came out of my PhD thesis at Berkeley in 2003. But earlier, there had been some ideas related to that. So what if I try to do PCA? Is there a way that I can do it by factorizing a matrix? And so there was a lot of work on matrix factorization. So advantages is closed form. In theory, if you really are a pure mathematician, it's great. You can, this solves a problem for arbitrary many dimensions. You can potentially estimate the number of subspaces, their dimensions, everything comes out of it. Okay? But if you're an engineer, the price to pay to get all of that is exponential complexity on the number of subspaces and their dimensions. So computationally, I guess people that do algebraic geometry and compute with Grosvenor bases know that there is a lot of issues regarding that. But the other issue with most algebraic techniques is sensitivity to noise. Think about computing the roots of a polynomial in one variable. You perturb the coefficients. That has a huge effect on the roots of the polynomial. That's what I'm talking about here, exacerbated, because these polynomials in several variables and factorization is not just computing the roots as in univariate polynomial. The other issue is that this does not accommodate for missing entries. So it can tolerate some noise, but not a lot of missing entries. Right? So by the end of 2005 or so, even though this was great and we could use this to initialize the previous techniques, we were really looking after something else, primarily due to robustness and complexity. And that, I think, is where spectral clustering-based methods sort of took center stage. And so what was the basic idea of spectral clustering? It was, well, let me just build a graph. Every data point becomes the node of a graph. All right? And then I'm going to connect pairs of points depending on how similar they are. Typically, similarity depends on distance. If we are close to each other, we are similar. And then this becomes a weight connecting pairs of points. Right? That's similarity. Typically, the similarity is between 0 and 1. 0 is no connection. 1 is we are very similar to each other. And then there are techniques from spectral methods, and you might have seen some of them yesterday, that allow you to cut this graph into multiple subgraphs corresponding to different groups. Okay? But the challenge is building this similarity. As I said earlier, points are very far apart. I would like them to be in the same group, but I can't make them be in the same group. Okay? So some techniques were very local. So how could you build these similarities in a local way? Well, you could say, let me take that point, I'm going to take the k nearest neighbors, right? Unless I'm very unlucky, likely they're going to belong to the same subspace. Likewise, I can take this point and its k nearest neighbors, and very likely they're going to belong to the same subspace. So now I can estimate maybe a normal locally and another normal, and the angle between those normals is going to be a pretty good similarity. Okay? And so that's essentially the basic idea between a variety of local methods that look at points, nearest neighbors, and try to decide how similar points are. But that fails, of course, near the intersection, because you can have neighborhoods that are now mixed. Go back to my example on faces that I told you, right? Faces, you look at 10 nearest neighbors, 65% of them are in the wrong group. So that's the case where this is going to fail. The other fundamental problem with spectral clustering is that it's predicated on this idea that of affinities. I just take 2 points and I say how similar are they. In this particular case, how likely it is that they belong to the same subspace. And now from a mathematical perspective, I ask you, is that actually possible? If I give you, say, suppose that it was a plane at dimension 2, and I give you 2 points, and I ask you, do they belong to the same plane? What would be your answer? Always yes. I can always pass a plane through those 2 points. So if I give you 3 points, can you pass a plane through them? Always yes. So the only time that you can start asking this question is if I give you 4 points, I can ask you, are they coplanar? And now the answer might be yes or maybe no. So the fact of the matter is that looking at 2 points alone, I cannot tell you if they're in the same group or not. I need to look at a point, actually many points. If the subspaces are of dimension d, for instance, I need to look at d plus 1 points if they're linear, or d plus 2 points if they're affine. Okay. But what does that mean? Now it's combinatorial again, because I need to look at a point and any possible choice of d plus 1 neighbors that might be in the data. So that's n choose d approximately. Okay? So again, if I try to do this globally, it's really combinatorial and very problematic. So these local methods, in fact, is rather than looking at all possible other neighborhoods around you, they're saying restrict yourself to your nearest neighbor. And that's the way they bypass the combinatorics. But by doing so, you end up with the problems with mixed neighbors, right? So that's exactly what leads to the advantages and disadvantages of these methods. On the one hand, the local ones tend to be efficient, right? The global ones are more robust because they really look at the structure of the whole data to decide. But local methods have this issue of sensitivity, but the global methods are intractable, computationally complex. So there are pluses and minuses, and they're very complementary when you look at local versus global methods. The other issue is that in general, although there is research here, you need to know a priori how many subspaces there are and what are their dimensions. Okay. So this went on 2006, 2007, 2008, 2009, and we were frustrated by this dichotomy of do I go local, do I go global? In one case, computationally complex. In the other case, I can make a lot of errors. So which way do I go? Up until in 2009, we made this discovery that forget about nearest neighbors, forget about locality. Look at every possible other data point. In principle, you might say, well, that seems silly. It's going to be very complex again. But as it turns out, the key insight is that the data is what I call self-expressive. Namely that all of points in the same subspace are very happy to write as each other as linear combinations of each other. Because if I've got a subspace of dimension d, I just need d points, and all points in that subspace can be expressed in terms of only d points. Okay? So the key idea was to look at this property of self-expressiveness and say write points as combinations of others, but select very few. And very luckily and very fortunately, the very few you select are always in your own group. I'll discuss that in more detail, the mathematics, in a minute. So for now, believe me. And so as a consequence, the big lack was that you can get these nearest neighbors, but not in the usual sense based on distances, really based on membership to the same subspace by solving a convex optimization problem. Think of least squares, maybe with some variance, with L1 norm instead of L2. I'll discuss those in a minute, okay? But by and large, by solving sparse and low rank or least squares type of problems, you can get these affinities now globally, and you can therefore solve both problems. So as I said, some techniques come from sparsity, some from low rank. There is lots of work on trying to put the both of them together. And the big pluses is that they're efficient, although I'm going to put that with quote unquote in a minute. Solve convex optimization problems. The other key advantage is that they turn out to be really robust. You can corrupt the data with outliers, you can corrupt the data with corrupted entries, and they work very well. Not just in practice, there is a lot of theory, and here are some of the papers of Candace proving that you can tolerate outliers, that you can get perfect reconstructions or with overwhelming probability for the more probabilistic one. Right? So what are the minuses? That all the theory, all the mathematics supporting the correctness of these methods assumes that the dimension of the subspaces is low enough. Okay? And the other one is that even though there is some research, and I'll touch upon that in a minute, missing entries still seems to be a very hard problem. Subspace clustering and missing entries are the same. Okay? So if you're interested, I wrote a tutorial a couple of years ago, and many of these methods are discussed and compared. And so you would say, well, we are done. The problem is solved, and there is no need for a workshop today. So what's going on now? I opened my talk by saying big data. And so how well can we do? Well, that algebraic technique that I talk about, I told you was exponentially complex. At the time of my thesis, I did most of my experiments projecting the data to dimension 5. 5 years after, my students are better or the computers are better. Now we can maybe do 10 dimensions or 11, maybe 20, in that order. Order 10. And the number of points might be around 1,000, maybe more, depends on, okay. I'm just talking, you do it in your laptop. The sparse methods, on the other hand, we've gotten it to about 10,000 dimensions, 10,000 data points, although we really like to project those faces to only so many thousand dimensions, because otherwise we can't handle them. So very recently, there was the proposal of, instead of doing L1 minimization, why don't you do a very old technique in sparsity called orthogonal matching pursuit, OMP. And my student, Chong Yu, who is here, and you can talk to him if you want to learn more details, has shown not only that you can get to about nearly 100,000 data points right now, but also actually prove theoretical guarantees of OMP. They're not as good as those of SSC, but they're pretty good in fact. So I think the challenge is to get to 1 million data points in 1 million dimensions. And I think methods aren't there yet. The other challenge I'd like to identify is this challenge of missing data. We had in our original paper in 2009, oh, this is the way we handle missing data, but it was just, a little bit of an algorithm there. There are cases where it works very well, cases where it fails, no theory whatsoever. Erickson, Balzano, and Pimentel will probably tell you today what is really the state of the art in these types of methods. What is the fundamental challenge? Why don't you just do low rank matrix completion, which has been very well studied problem. The problem is that you have a union of subspace, not just one. And if you have many of them, the matrix could be full rank. So in fact, all of matrix completion, low rank matrix completion would fail. So you really need to look at this union of subspace structure put together with missing data. And so there is a lot of open problems in there. Kong Yuan Yang, one of my students, you want to talk to him, he's working on this problem here today. All right. And here's another thing that's going on. So another of my students, Manoli Sakiris, started to work on this problem maybe about 1 year or 2 years ago, and did something completely unexpected to me, and that it was a direction that was not sort of the natural next step. So what do you think he did? The return of GPCA. He looked at the key issues with GPCA, one of them being robustness to outliers, robustness to noise, and he was able to come up with more advanced algebraic geometric techniques based on theory of filtrations that have been able to resolve many of the issues with robustness. We're still stuck at the computational complexity, but he has another year to finish his PhD thesis. So next year I hope to report on that. All right, so that was the introduction, broad overview of all methods. So let me now zoom in just into two specific methods. The first one, and that last slide I think it's very good, is the generalized PCA. So what is the basic idea behind these algebraic techniques? This is a plane, that's the normal vector. Assume that they're all linear subspaces. So B transpose X equal to 0 is the equation of the plane. Okay? If I have a line, then I can pass one plane through it with normal V1. I can pass another plane through it with normal V2. So more generally, linear algebra 101, subspaces can be described in terms of a set of linear equations. But I would like to change, and I like to say, don't say linear equations, say polynomials of degree 1. Okay? So subspaces can be described with polynomials of degree 1. What about a union of subspaces, right? That was the case of one subspace. So what if I now have two? So I've got B1 and B2 are the two normal vectors. And this is the equation describing it. Either I belong to the first group or I belong to the second group. And that was the reason for that chicken and egg dilemma. Do I do segmentation? Do I do estimation? Do I alternate between the two? Is because you've got this or. That is the source of the non-convexity of all the optimization problems. And as I told you, the key question was, how do I get rid of that? And getting rid of that or was very simple. You just do multiplication. So if the product is 0, one of the factors must be 0, and therefore you must belong to one of the subspaces. That was the key idea. And so, more generally, I've done this for two planes here, but the general theme is that a union of n subspaces can be described as the zero set of polynomials of degree n. And these polynomials of degree n are not arbitrary. They have this very special structure. They factorize as products of linear factors. All right? More importantly, each linear factor encodes a normal vector to each one of the subspaces. And that is why I said at the beginning that the key idea here is take the data, fit a polynomial of degree 2 or 3, whatever the number of subspaces is, and then factorize that polynomial. Okay. How do we do all of these? So the first one is the estimation of the polynomial. So we came up with the lousiest way to do it, and no one has done it better since then, so I'm looking forward to a better solution to this. Just take that polynomial and expand it. So if this was two lines, so we have polynomials in two variables, x1 and x2, this is just something with x1 squared, something with x1, x2, something with x2 squared. So there are three coefficients here, and you can always write this as the dot product of the vector coefficients of the polynomial and the stack of all the monomials of degree n that can be formed in all of your variables. And that is what in algebraic geometry is known as the Veronese map of degree n. In machine learning, this is known as the polynomial embedding, and is heavily used in techniques in kernel type math. So how do we fit these polynomials? Well, if I have n data points right now, each one of them, I generate all of the monomials. So this is for the first data point, for the second, for the n. And I put them all as rows of a matrix. That's what that matrix L is. We call it the embedded data matrix, because it's take your data, generate all of the monomials of degree n on your data. That's what L sub n stands for. And the vector of coefficients, because of this equation, needs to be in the null space of that data matrix. So how do you find your polynomials? You compute the null space of the embedded data matrix. Right? That's what. Why is this a bad method? Well, it's the reason we did it this way is because now it's least squares, right? I don't need to worry too much. But the fact of the matter is that there are lots and lots and lots and lots of possible monomials that you can generate of degree n in d variables. That is why this becomes exponentially hard. It's least squares on way too many coefficients. And the reason is because this approach neglects the fact that the entries of C are not arbitrary, but they come from just the original normal vector. So there are nonlinear relationships among the coefficients that are neglected by this least squares type of approach. As it turns out, algebraically, you can also determine how many subspaces there are. And the way you do that is by varying the degree. Insofar I said you have 2 subspaces, you will do it with polynomials of degree 2. What if you don't know? Well, what you do is that you try all possible cases. So you try degree 1, it didn't work. You try degree 2, it didn't work. You try degree 3. The first time it works, what do I mean by work? The first time that this matrix drops rank, that is when you have the right number of subspaces. Okay, so I've convinced you that there is a lousy method to go from data to polynomials. So now I say that I have all of the coefficients of my polynomial. How do I get the clustering? How do I get the original subspaces? So I need to go back from the coefficients to each one of the n factors. And this is what I've illustrated here. Okay? So one way to do it is to resort to algebraic geometry and go and try to find how do you factorize homogeneous polynomials of degree n that factorize into linear factors. And that's what we did first. So our first algorithm in 2003 was precisely based on just factorizing the polynomials. But as I argued earlier, this is very sensitive to noise. As soon as the data is corrupted, your coefficients are computed with least squares, they are perturbed. What if you get complex roots in your calculations? Everything goes wrong. Okay? So those are the issues that happen over there. So fortunately, 1 year after, we were a little bit smarter than the first year, and we realized that actually you can solve these with calculus 101. Maybe calculus 3. If you compute the derivative of a polynomial at a data point, that gives you a normal vector that you were looking for. Okay? So instead of doing pure algebraic geometry, which is go from polynomials to the factors, this is use the extra information. You have not only the polynomials, but you have the data as well. So if you evaluate the gradient at a point, it gives you normal. Why is that true? Well, your algebraic variety, or your union of subspaces, you think of it as just some algebraic surface. Right? It's very strange because it has this union of two subspaces, but it is a surface. If I have an equation for the surface, that's what the polynomial is. P of x equals 0 defines the surface. If I take one point and I compute the gradient, it needs to give me a vector that is orthogonal to the surface. Because this surface is very peculiar, it's a union of planes or a union of subspace, it has to be orthogonal to the plane that is there. So that is why the normal to the subspaces can be obtained just from the gradients of the polynomial. Okay. And so that actually works much better, and it works with real data. It works with corrupted data with some moderate level of noise, but again, it fails when you have outliers, for example. So to summarize, what is the basic algorithm? You take your data, you embed it into polynomials of degree n, that gives you the embedded data matrix. You compute the null space. In some cases, you can get the number of subspaces by exploring the rank of the matrix, and then you take these derivatives of the polynomials to get the segmentation. Okay, so that was the end of the first part. Let me see how I'm doing. Second part, as I said, the main frustration was exponential complexity. The second frustration was robustness, and so we needed to look for something else. And we went through this idea of spectral clustering. As I said earlier, you simply take the data, you build a graph. Each data point is a node in the graph. You connect pairs of points with some similarity. And by looking at the Laplacian of the graph, you can get the segmentation. cutting the graph is equivalent to computing the null space of a Laplacian and doing k-means on the eigenvector. Okay, but the issue is how do you come up with a good affinity? And I made this point earlier already. Points that are very far, I want them to be in the same group, but the e to the minus the distance will not do the job. So I would like points in the same subspace to have very large pairwise affinities, and points in different subspaces to have 0 affinity. That's my goal. How do I do that? Okay. So here was the basic idea. Self-expressiveness. If I take a data point, I'm going to write it as a linear combination of all other data points. Okay? So that's data point I, data point j, cji is the coefficient relating these pairs of points. Okay? In vector notation, the vector y is equal to the data matrix times this vector of coefficients. This vector of coefficients is now of dimension n, where n is the number of data points. Or in matrix notation, the data matrix is equal to itself times a matrix of coefficients, and that matrix of coefficients is now n by n. Okay. Good. So data are self-expressive. Find now a good affinity C. Well, that equation, I look at it, the identity seems pretty good. Right? It's a solution. The identity is a solution, right? Is that a good affinity? No, that means that I'm very selfish. I pick myself as the only, right? So that's not going to be very good for clustering because every point would only connect to itself. So I need to prevent this pathological case by saying you're not allowed to pick yourself. No self-nominations allowed. So let's look at this picture. Suppose that you tell that green point that he's allowed to express itself in terms of all the others except for itself. And suppose that I tell you, look for a solution that is sparse. You want the smallest possible number of non-zero coefficients. Okay? Okay. Then, what would be the sparsest possible you can do? Suppose that that is the origin. What is the sparsest you can do? If I tell you, write that green point in a linear combination of the other 100. Can you do it with 100 non-zero coefficients? Yes. 50? Probably yes. What is the sparsest you can do? Anyone else? So if this is a line, it goes through the origin, then that green point is a scalar multiple of any other green point. So one non-zero coefficient is enough. Okay? 1. Interestingly, 1 is the dimension of the line. And in fact, any green point will do. There are many possible solutions to this. But all of them give me what I want, which is selecting another point that is in the same group that I'm in. So among all the sparse solutions, any solution is equally good. Right? Is this always true? Well, suppose that I take now this green point and you say I'm going to write it as a linear combination of everybody else. Again, I could do it now with dimension 2. I can always write a green point as a linear combination of any 2 other green points. Right? But here's the trick. It could have been the case that that green guy is a linear combination of that red and that blue. So still the sparsity level is 2, but I got very unlucky here. It comes from 2 different subspaces, so it's not going to work. So from a mathematical perspective, the question was, when is it the case that if I write a point as a linear combination of all the others, and I ask for a sparse solution, the sparse solution will have the property that, 1, the number of non-zero coefficients is equal to the dimension of the subspace I belong to. 2, the non-zero coefficients correspond to points in the same group as another. That is the basic mathematical question. The second mathematical question is, I am a lazy person. I don't want to do smallest number of non-zero coefficients because that's L0, that's NP hard, and complex. So I'm going to be lazy and I'm going to do something else. L1 is one option. Orthogonal matching pursuit is another option. Pick your favorite sparse method. So then from a theoretical perspective, for each method that you pick, say you pick L1, you ask the same question. Does the L1 method give me a solution that has that property? Number of non-zero coefficients is equal to the dimension, and non-zero coefficients correspond to the same. And so as it turns out, the answer is yes, but under some conditions. So one condition, and this was the very first one, and it's the strongest of all, says that if the subspaces are independent, which means that the dimension of the sum is equal to the sum of the dimensions, then this is always true. Okay, so in particular, one line plus another line, 1 plus 1 is equal to 2, which is the dimension of the ambient space. That's what this condition says. The dimension of the sum, 2, is equal to the sum of the dimensions. 1 plus 1 is equal to 2. Okay? But that's a strong condition, so it will not cover cases where things are dependent and there are lots of intersections and things like that. So a lot of the theory over the last few years has been, can you look at the case of dependent subspaces, and can you come up with theorems that tell you when this works? So here there is a lot of math, so don't read it, just pay attention to what I'm going to say. The key quantity seems to be what is the angle between two subspaces. And what this theorem effectively says is if the cosine of the angle is small enough, which conversely means if the angle is large enough, this is going to work. The other one is more complex to explain, so forget about it. But effectively what it says is that the data needs to be well spread out and well distributed in the subspace. Okay? So the conditions then is if the data is well spread out and the subspaces are sufficiently far apart, L1 minimization works and it gives you the right connectivity. And there's been lots of really great work by Emmanuel Candes trying to actually do this in the probabilistic setting. The subspaces are drawn at random, the data is drawn at random, so the theorem is with overwhelming probability, lasso, which is the regularized version of this, will give you a solution that gives you the right class structure. Okay? And there are theorems also, this is the theorem here, is all noiseless. There are also theorems now of what happens if the data is corrupted with outliers. And the theorems are, if the percentage of outliers is small enough, then this works. With noise, the idea is that you need to put together the noise with the angles. Because evidently, as soon as there is noise, you can tolerate angles that are, you need a bigger angle to compensate for the noise. So all of these theorems now exist, and is great work that has happened over the last 5 years. Okay, so the summary of it now, algorithmically, is you take a data point, you express it as a linear combination of the others. You don't do this exactly anymore because you've got noise, and so you do lasso, and you do L1 minimization, or your other favorite technique. I will skip how you handle outliers and noise in this period of time. All right, let me conclude in the last minute or so with a few applications. So I will mention the one that I've motivated so far, which is segmenting videos of multiple moving objects. I will talk also about the application that I mentioned at the beginning, which is clustering faces. And I will skip this one, but this one is pretty cool. What if I give you a very large data set and I tell you pick a few examples that are representative of the entire data set? This can also be done using the same type of techniques. So the first one is I give you a video like this one. So there's a car, the camera is moving up and down. You use computer vision techniques and you're able to extract these trajectories as a function of time. And the task is to go from these trajectories that you don't know which one corresponds to which moving object to this picture where it's now fully labeled. Okay? So in this particular case, what is the data? The raw data that is the input to the algorithm is these trajectories. So these trajectories are vectors, and their dimension typically is 2 times the number of frames. Why? Because each point is 2-dimensional, and you track it through the entire video. So 2 times the number of frames. And in this case, the dimension of the subspaces is 4. So all of the trajectories associated with the car, that's 1 4-dimensional subspace. All of the trajectories in the background, another 4-dimensional subspace. So this picture here shows what is the clustering error. So the y-axis is what is the percentage of trajectories that are erroneously classified.
And the x-axis is the index. So there are 155 videos. I'm showing here only the largest errors, from 90 to about 155. And so what is this number right here? This number is about maybe 30-something%. So that is the worst possible error. So these errors are sorted. So among the 155 videos, the video sequence in which you make the worst error is 35%. That's what this means. Okay. So the yellow curve here, that is my PhD thesis. All right? That's what I did. The red curve here, that is the return of GPCA. Okay? So that has been the progress of the last 15 years. So the moral to the story is always hire good students. The black one here, that is the sparse subspace clustering, which was the best method up until recently. But the very interesting and very unexpected fact is that we always believed that the algebraic was never going to work, but now we were able to make it work even better than the sparse techniques, which were pretty good. Okay. And everything in between is many of the methods that have been developed between 2003 and 2015, which I reviewed earlier. Right? These are some of the examples, Obama from the left, Obama from the right, so 1 or 2. These are 2 different groups, right? And it's, you can see how automatically is determining which view it is. Here, it was the same idea on the debate as switching from multiple. Let me maybe put it back. Sorry. And the last example is clustering phases. So in this particular case, this is a well-known database. There are 38 different people. There are 64 images for each subject. The y-axis is what is the error in clustering, and the x-axis is how many subjects there are. I should have updated the slide. We have done it for the 38, but here I'm only showing up to 10. Okay. What is a method that did not work well? This one over here. That is a method that is based on this local. Look at your nearest neighbors. Are they in your own group and form your affinity? I told you for phases that's no good because 65% of your nearest neighbors are in the wrong group. That is why this method doesn't do well. Okay. The blue one here at the bottom, that is the sparse subspace clustering method. That's the best. Notice that the algebraic is not there. Why? Because we can only do up to 10 dimensions. And if you take phases and reduce it to 10 dimensions, it's too aggressive of a dimensionality reduction. Okay, so there is still a caveat, which is the computational complexity. So, in summary, I hope to have convinced you that subspace clustering is important. There are many applications of it, not only in computer vision, I illustrated them, but there are many others. And you will see many throughout the talks today. I've shown you 2 different techniques today, one algebraic, the other one based on sparsity to tackle the problem. And the interesting thing, particularly of the sparse method, is that they come with theorems. They tell you under what conditions the clustering is right, which is not the case of many of the algorithms. Thank to many of my collaborators. Most of the algebraic work was done originally with Yima and my supervisor Shankar Sastry at Berkeley, and Manolis is currently a student working on that. And most of the sparse work was done by Ehsan El-Hamifar, now at Berkeley as well. And low-rank work has been done with Paolo, and Chong is currently my student working on OMP for this problem. Thank you so much for your attention.
Video motion video.
Yes.
Video motion animation. Here.
This one? Yeah.
I see the no.
Yes,
No, no,
I
this one.
like to move. Okay.
Actually, you removed a lot of pixels with very hard motion identification around car. So the question is whether you run algorithm for those pixels or for entire pixels or regular. Because I know that if you add those pixels from the row, not from the type, not from image inspection, you will have problem. I don't know what do you use for this.
That's really a fantastic question. So these points are not obtained manually. There are computer vision techniques that you run on the videos to extract. And typically, you extract regions that have high spatiotemporal gradients. All right? Because those regions are easy to track. If you have a totally wide screen, you can't know what moved to where. Okay? So because of the tracking, you cannot track every point very well. So that is why these trajectories are sparse. It's also inspired because most of the research in computer vision in the 2000s was trying to do 3D reconstruction by looking at these trajectories. But you're totally right. So the technology today is if I'm able to track every pixel, if I can get what is called dense trajectories, does this work or does this not work? So there are two issues with that. One is computational complexity because now you have many more data points. But the other one is that trajectories start to be very close to each other. And therefore that makes the classroom problem challenging. So in fact, my student is exactly working on that problem, especially for motion of people, where you can actually get those dense trajectories. And I don't know of any work today that is able to solve that problem very well.
For the sake of time, I think we are a little bit behind schedule, so I'd like to thank Dr. Udall again.